Good day, grade 11s. Today we're going to do a quick revision over the concepts regarding electric circuits. Now, when we deal with electric circuits, there are a couple of key things that we need to remember. First of all, we need to look at the potential difference. We're going to look at the resistance. There's a distinct relationship between the two, and therefore we're going to look at Ohm's law as well. From there, we're going to move into the type of components that we have in the circuit, the relationship, drawing your circuit diagrams, and we're just going to, for the interest, look at ohmic, non-ohmic conductors, and then also at the energy exchanges that take place inside a circuit when work is done. Let's start off. Some of the key concepts that we deal with in this session, as I said, we will be focusing over here on your resistance. We're going to look at Ohm's law, the relationship that we have between resistance and Ohm's law, ohmic, non-ohmic conductors, and then very important over here is the series and the parallel connections that we have inside a circuit. With energy and electric circuits, we're going to look at calculations and how we're going to implement those into furthering our studies of electricity. Let's start off with conductors. Now, most metals are very good conductors. By definition, we want to work with a conductor that does not heat up a lot, because the warmer the conductor gets, the higher the resistance of that conductor. That is referred to as an ohmic conductor. Now, metals are very, very good conductors because they have electrons that move around freely. Earlier on in the year, we did a section on semiconductors where we looked at the band theory. So just a quick revision for you over there on the band theory. When we go and we look at our metals are forming crystals which are referred to as a metal lattice, whereby the positive particle of the metal atom, which is known as the cation, are situated in a crystal-like structure where they are closely packed together. Now, these electrons that surround the atom are allowed to move around freely, and we refer to those as the sea of electrons, as they are moving around freely between the atoms and can very easily move from this position to that position in the structure that we have. Now, from this structure, if we go and we look at it in more depth, we will see that we have what is known as a conduction band, and underneath that we have the valence band. Now, the valence band is the area where we find our valence electrons. Now, remember, the valence electrons are the electrons that are found in the outermost energy shell of an atom. With non-metals, there is an energy gap that exists over here, which makes it impossible for the electrons to jump into the conduction band. The conduction band is almost like a highway or a conveyor belt for electrons, whereby they are allowed to move around freely. Now, if it is a non-metal, they will have a huge, big energy gap over there, and the electrons cannot move around freely. But the moment we start dealing with metals, we find that this gap over there completely disappears, or the conduction and the valence band start overlapping. This means that it is now very easy for my electrons to move from the valence band into the conduction band. No increase of energy, heat, electricity is needed, and these electrons move into the conduction band, allowing the metallic substance to therefore go and conduct electrons or electricity. So that is the prime reason why they make up good conductors, because the electrons are loosely bonded and can easily move around. The second type of conductor that we have is solution. Now, for a solution, we need to have, or a solution is called an electrolyte. And inside the solution, we need to have positive ions as well as negative ions. Now, these positive and negative ions are found in an aqueous solution. Remember from the chemistry section where we looked at ionic compounds, that when they dissolve in water, dissociate to form positive and negative ions. These are the ones that therefore go and conduct electricity. The positive ions are attracted to the negative side of your terminal. In this case, if you had a carbon rod in there, it would be attracted there, and the negative ions would be attracted to the opposite one, the positive rod. And that causes then the movement of charges within the solution, which is therefore the conduction of electricity that takes place within a solution. Insulators are defined as any substance that inhibits or stops or prevents the movement of charges. By definition, most nonmetals are very good insulators. That would be compounds as well, glass, ceramics, plastic, wood, paper, cardboard. The reason for this is if you go back to what the picture that we had earlier on, where we have the conduction band and the valence band, the moment we have that gap for a non-metal and the electrons can't transfer over there, the electrons stay fixed over here in the valence band. And that makes it an insulator, and the electrons cannot move around. The only exception we have over there is your semi-metals, whereby when we have doping, they will, depending on the type of dopant, be able to move electrons around, and these semiconductors are used in electronics, where when the temperature increases a lot, the flow of electrons take place very easily. Current electricity is defined as the movement of charges. By definition, you should remember that the only charged particle in an atom that can move around is the electron. So therefore, the charges that move around in an electrical circuit are the electrons, which carry the negative charges. A closed circuit allows current to pass. Remember, these electrons are not Olympic athletes. They can't pole vault from one section to another section. So if there is an opening in your circuit, no matter how big or small, the electrons cannot move from the one side to the other. You need to complete the circuit, close that opening, and then the electrons can move around in a completed circuit and go from the positive to the negative terminal of the energy source that you have connected to your circuit. The movers and the shakers of electric circuits are known as the electrons. These electrons carry with them energy. And as you know from our studies on electricity and energy in chemistry as well as physics, you would know that we have different types of energy. You've got kinetic energy, which is movement, and you've got potential energy. Now, these electrons contain potential electrical energy, and the apparatus that we use to measure this energy is known as the voltmeter, because it measures the potential difference. Remember, this difference is the difference in the potential energy on the one side of your resistor to the other side of the resistor, from the one end of your circuit to the other end of your circuit. And if it is a cell or a battery, it would be from the one terminal to the other terminal of the cell or the battery. Now, by definition, the potential difference is measured between 2 points, and it is known as the work done by 1 coulomb of charge when it moves past a point from one section to another. Remember the idea that I sketched over here, that if you have potential difference, that it runs from one end to another end, and you go and you compare the initial and the final potential energies for that. Okay, if we go and we insert over here our resistor, which is going to use that energy, it is going to do some work, and the apparatus will always be connected in parallel like this, where we then go and we insert our voltmeter, measuring the energy going into our resistor over here and coming out of the resistor. So it actually takes a reading of how much energy we had previously and after the energy was used up by our circuit component. Resistance. Now, the relationship between potential difference and resistance comes in the fact that a resistor will use the energy that is harnessed by the electrons. The higher the resistance of the component, the more energy is used up. It does not reduce the number of electrons. The number of electrons inside the circuit will remain the same. It is just the energy that each of these electrons carry with them that becomes reduced. Imagine going on holiday and having a backpack full of sweets on your back. you are going to, during the course of the day, use up some of that sweets to provide your body with energy as you climb the mountain. Now, in the same fashion, that electron carries energy with it. And as it moves through the resistor, like you would go traveling through the mountain, it uses up the energy. So at the end of that session, the electron has less energy, just like you would have less sweets in your backpack after taking a long hike. Now, resistance is caused by the collisions that occur inside a conductor. Remember, these collisions, when they occur, use up energy, and that is how the energy is used in the resistor. Moving on to the relationship between resistance, we're going to look at Ohm's law. Now remember, the relationship between resistance and potential difference is the moment you have more energy, there's more energy available in the circuit, but the usage of the energy depends on the resistor. One thing we haven't mentioned much is your current. Now, current would be the charged particles that move around in the circuit. As these particles move around in the circuit, they carry their energy with them, giving it to the resistor that needs it, and then moving on. We would notice over here that by definition, Ohm's law is looked at as the current between 2 points in a conductor that is directly proportional to the potential difference between these 2 points, provided that the temperature stays constant. Now, the reason why it is so important that the temperature remains constant is the fact that temperature is related to resistance. An increase in temperature means that there is more resistance in that particular resistor. If your resistor increases in resistance because of the temperature change, it is going to consume more energy, and that will therefore affect the total energy inside the circuit. The equation that we have over here is the following, where R stands for your resistance, which is always measured in ohm, potential different, measured in potential different in voltage, and your current, which is measured in ampere. Now, please be careful, because I know we all get excited, we start writing the exam, and then we start swapping the units with the calculation symbols. All right, current is an I, and not an A, where your potential difference is a very lucky one. The voltage, or the volts, and the symbol over here are exactly the same, and then R would be your resistance. We also make sure to always go and refer back to your information sheet or your data sheet that is given in the exam. It might happen that this formula is given in a slightly different variation, where they might give you the formula as V is equal to I multiplied by R. Both of these formulas can be used to do calculations, as they have all of the relevant variables in there. As I mentioned, the resistance depends on 3 things. The type of material that is used. If you go and you look at the type of material, and we go and we compare, for instance, nickel with gold. Nickel has got a very, very high resistance, whereby gold has got an exceptionally low resistance. That means that gold would be the ideal conductor in our households. But unfortunately, as we know, gold is a little bit expensive, so we're sticking to copper in South Africa. The length of the conductor. Now, the longer the conductor, the higher the resistance. Come on, boys and girls, let's be honest. If I have the choice between running 10 meters and running 10 kilometers, I'm going to choose the shorter one because it offers less resistance. Now, the same thing applies to the resistance of a conductor. If I increase the length, I'm going to increase the resistance. Third one, the thickness. If I have an extremely thin resisting wire, then I will notice that it offers a high resistance, and it is most likely going to heat up very quickly. If I increase the thickness of the wire, it will not heat up that quickly, and the resistance should remain lower. For that reason, if you go and you look at light bulbs, the filament in a light bulb is a very, very thin piece of wire that is wound in circles so that it decreases the length, but once you stretch it out, it becomes a really long, thin, skinny piece of wire, which has a very, very high resistance. And the reason why it requires this high resistance is so that the metal can glow once electricity passes through it, lighting up the entire room. The last factor that we need to look at over here is the temperature. Now, the temperature is very important. In most scenarios in the lab, we try and we control the temperature of the resistor. This allows us to take accurate readings once we do our calculations. Now, in real life, that does not always happen like that. We also sometimes go and we use the fact that the resistor heats up to improve our daily life. If we go and we look at appliances like ovens, let's just try and rewrite that one, like ovens, kettles, heaters. All of these appliances use the fact that a conductor increases with temperature when there is resistance. So the resisting wire, the resistance over here, will cause an increase in temperature. This increase in temperature is useful to us and it makes us very happy because our oven will work. I can go and cook that meal when I get home tonight. It will boil the water for my cup of coffee, and in winter it's going to keep me warm. But if this device was something that I needed to keep cool, like for example a computer, I would not want my computer to heat up excessively. So with your computers, we stick to metals that have a low resistance and therefore a low temperature. Now, apart from the basic operational value over here, it also has certain safety precautions, and that is why we try and keep the temperature as low as possible for these devices. Now, going back to the temperature, the change in temperature that we encounter over here also gives rise to two different types of resistors that we have, and those resistors are referred to as ohmic and non-ohmic conductors or resistors. Now, when we talk about an ohmic resistor or an ohmic conductor, that refers to a conductor or a resistor that ascribes to the Ohm's law that we looked at earlier on. That means if I apply the current, potential difference to my resistor, the temperature will remain roughly constant. So the conductor will maintain a constant temperature. Okay, let's just get clarity on this. If I'm talking about the element in my oven, or the stove plate, or the kettle, those would be ohmic conductors, because as they heat up, except for the kettle, as they heat up, the temperature stays constant once it has reached a specific temperature, and the resistance for that element stays the same. If I go and I look at a non-ohmic conductor, these ones change slightly, and they have to go through an increase in temperature over a very short period of time. An example over here would be the filament in a light bulb. Now we know that when you switch on the light, there is light immediately, but on a microscopic level, what happens over there is that initially the filament is quite cold. Electricity starts rushing through there, heating up this element. And as the element, or the filament in the bulb as we call it in science, starts heating up, it starts glowing first with a red and orange light, and then with a brilliant white light as it heats up. These are your non-ohmic conductors, and we can look at them in the following fashion. When they go and they form a graph, firstly, let's look at the relationship over here between the resistance and the potential difference for an ohmic graph. Now, your ohmic graph over here will form a graph that is known as a straight line. That tells us that as the resistance increases, the potential difference, or the electricity that is used, will also increase. So we can see that over here. It starts through the origin and it produces a straight line. Our non-ohmic conductors do not follow this. We will notice that initially they heat up slower and then they go and they follow the straight line. So over here in the beginning, it is a slow increase of the temperature, which is not constant. Only much later on do we find that the relationship between the resistance and the potential difference is then a direct relationship, whereby the increase of the one will lead to an increased consumption of the other. All right, so that is therefore that small difference between the two graphs of the two when we deal with ohmic and non-ohmic resistors. Circuits. Now, dealing with a circuit can become either your biggest problem or the biggest area where you're going to score marks in the exam. Circuits are not that difficult. They require logic thinking and a cool, calculated approach. I always advise my school kids to pack out the pencils and use as many colors as possible when they work with circuits. Because when we see it in color, we also understand what is happening a little bit better. We need to remember a couple of key concepts while we are busy over here. The first type of circuit that we deal with is known as a series circuit. If we look at the circuit over here, which is set up on our board, this is a classic series circuit. Now, for a series circuit, these are some of the requirements. All of your components are situated in a cyclical fashion. So the one follows on top of the other, and if I had to go and take this and stretch it out, they would form one line of components. So in a series circuit, we will notice the following. The current will remain the same throughout the circuit. If I go and I look, the current that passes from here to there will go through this component. It will carry on past that component, through all the way right through my ammeter back there. Now remember, the current refers to my charge particles. If my current remains the same, it means that the charge particles moving inside that circle remains the same. I'm not going to take some away, add in as I go along. Right, so they remain constant. The other important thing over here, you will see that I have got voltmeters connected over here. My first voltmeter is connected across the cell or the battery. Now this voltmeter gives me the reading for the entire circuit. And that is why we refer to it as VT, the T standing for the total. So in a circuit like this, we find that the total potential difference is equal to the potential difference of the individual voltmeters that we have over here. So V1 and V2 is going to add up to give me exactly the same potential difference that I had over here previously. So inside a circuit, the amount of energy that is used up by each component will add up in the long run to give me this total energy that I have given to me by my cell or my battery. The last component over here that we need to talk about is the resistor. Now your resistors over here are the two components that use the energy. You will notice that the voltmeter is connected in parallel across each one of these resistors. In a series circuit, the total resistance for my series circuit is equal to the sum of all of the resistors that I have in the circuit. You will notice that I use the footnote S instead of T. The only reason for doing so is the habit that I have of indicating that this is for a series circuit. It would be absolutely correct if you said that the total resistance for my circuit is therefore equal to the resistance of the two resistors that I have over there. Both of these are the same. That S just stands for series circuit. Remember footnotes. They are very important and they make your life easier. If you go and you ascribe footnotes to each one of your calculations, it allows your examiner or the marker to go and look at what you did and see, oh right, John over here decided that S is this value, and we can track what you have done. The way you set out your answer is an indication to us of what was happening in your head. So it gives us a guideline of your thought pattern and the method that you used when we mark your exam papers. Moving on to our parallel circuit, you will see this immediately starts looking more complex. There are more components and things are all together. Break it down, look at it systematically. If we go and we look, we will see that our current leaves over here. Now the current has a choice. The road splits up. Do you take the up or the down road? This particular group of charged particles chose to go that route. They follow their path and they go all the way back to the cell. At exactly the same time, another group of charged particles set out from the same battery. They move, since the top road is already taken, they now need to go and move through a different path. Here they join up again and they travel all the way back to the battery. Now you will see that in this colorful diagram that I have here, and this is why you need to use your colors, is you will notice it's a lot easier to see that the section at the bottom has a current that is different to the section at the top. These ones have the pink color line and the bottom one has the green color line. But over here, they are joined up. And there you will see, if we go and we look over there, the ammeter that is hiding away over here is going to give us a total ammeter reading. Now this total ammeter reading that we have over here has got to be equal to the ammeter readings for the two separate branches. So when we go and we look at a parallel circuit, parallel circuits are also referred to as current dividers. You will notice the divider refers to the current splitting up and dividing into as many branches as your parallel circuit has. All right, so your current divider over here tells us that the total ammeter reading, the total current in my circuit, is going to be equal to the current measured in each of my individual ammeters as we find them in our branches over here. Now these charged particles, when they leave the cell, have the same amount of energy with them. So whether they belong to the green line or they belong to the pink line, which is our two separate circuits that we have within the parallel circuit, all of these charged particles carry with them the same amount of energy. That means when they reach the point where they start splitting up, when they divide, those two different branches of charge will still carry their own energy with them. And that is the reason why in a parallel circuit, when we go and we look over here, the voltmeter reading, which is an indication of energy over here, is going to be exactly the same as the voltmeter reading that I have for each individual parallel connection branch over there. So inside your parallel connection, we notice that the voltmeter reading remains constant for each one of these branches. Be very careful though. Once we start dealing with networks and I start adding in resistors over here in my individual branches, then that might change, and we'll look at a scenario where we deal with that a little bit later. Now, the most difficult part for us to remember over here, let's make that one blue, will be the relationship with our resistors. Resistors in parallel reduce the total resistance of the circuit. The moment they are connected in parallel, the circuit becomes more effective because the electricity that is shared, the energy that is shared in each one of these is reduced. The calculation involved over here is a tricky one, so pay close attention. The parallel resistance, and I use the footnote P, is equal to the inverted value of resistor 1 plus the inverted value of resistor 2. This becomes quite tricky when we start working in calculations later on, and that is why I like teaching my children where we deal with this one to go and write it in a format that is familiar to you. And once you start working with your calculator, that format links up with your calculator and the calculation that you do. Remember, in an exam, you are going to be required to start off with the formula that is given in the information sheet. This is the formula for parallel resistance. So let's do a quick circuit over here and add in some values. If this is resistor 1, and resistor 1 has got a value of, say, 3 ohm, and parallel to this we have resistor 2, and resistor 2 has a value of 1,5 ohm. We are going to approach the problem as such. we are going to write out the original formula as given in our formula sheet, and then we're going to invert it because we want to make parallel resistance the subject of our equation. Once we invert it, what you do on the one side, you must do on the other side. But we do this using brackets. We are still going to keep it as 1 over R, and the value over there for 1R is going to be our 3 ohm plus the value of 1 over R2, which is 1,5. Close the bracket and invert it. Now when we put this into our calculator, it becomes really nice and easy because we are going to use the brackets and we are going to use the inversion button on our calculators. So we're going to open up the bracket, 1 divided by 3 plus the 1 divided by the 1.5. Close your bracket, and then we're going to press that fantastic, awesome little button over there, which inverts your entire calculation. So I've written it over there. It now shows up on my calculator. I press my equal to, and you see that the answer is equal to 1. Put that onto your answer sheet, and voila, your calculation is done. Instead of struggling with all of those fractions, because I don't know about you, I still remember being at school, fractions killed me. All right, so doing this process, going through all of these steps, it takes out the burden of struggling with the fractions. Just a couple of things that you must remember over here. Unit with your answer. It is of absolute importance that you guys remember to put units with your answers. If you leave out the unit, you're going to forfeit that mark. When you do this calculation, always start off with the equation that I gave in blue. That is your original equation. You get a mark for putting that down. You must also from there show a substitution. You must show that you inverted over here, that you are working with your parallel resistance. And the other key important thing to note over here is now that you've looked at our answer, you'll see that this resistance is less than any of the values that we had in our original circuit. And that is the beauty of a parallel resistance or parallel circuit. The moment you put resistors in parallel over there, the total overall resistance for that connection is less than that of the smallest component. So you can go and double check what you have done. If you do this entire calculation and this answer works out to be 4 or 5, you know you have done something wrong because your answer must be smaller than that of the smallest component in your circuit. Energy. Now, as I mentioned earlier on, all electrical circuits will use up energy. Depending on the resistor, it will be more or less energy. Obviously, the lower the resistance, the less energy will be used. The higher resistance, the more energy you will use. That is why it is going to consume less energy if you blow dry your hair because of the resistance of the hairdryer. But if you put on the oven and you leave it on for the entire day, the resistance there is much higher and your energy consumption through the electricity becomes a lot more, and that's going to push up your electricity bill. Now, the formulas that we deal with over here show the relationship that we have with the energy and the circuit in sense of the resistance for the circuit. Now, the key first one that we deal with over here is the potential difference and the work done that is done by the charged particles. Now, if you go and you look in your notes, you will see that right in the beginning, we talk about the potential difference or the voltage, and we say that that is the energy that is carried by each charged particle. So now we are going to look at the work that is done by each one of these particles as the charged particles move around. All right, so by the charge over here, you are going to divide that and it's going to give you your potential difference. Now, a couple of things to work from over here. Remember that this charge comes from the current multiplied by the change in time. Also, if we go and we change the equation over here, let's do that in a different color so you can see nicely. If I go and change this equation and I say work is therefore equal to the potential difference multiplied by the charge, you would notice that I would be able to go and substitute the Q in this formula. When I do that substitution, we will notice that my formula changes into V multiplied by I multiplied by the change in time. That is a different formula that you can go and use for your calculation. Again, go and look at your formula sheet. It might already be there. If it is not there, you can always work towards the formula when you go and do the calculation. Alternatively, we could have said, but my resistance is equal to my potential difference divided by the current. If I go and I change the formula, potential difference is current multiplied by resistance, I could have gone and in the original equation, I could have swapped around the current over here, the potential difference, not the current, over here. And I could have said, but wait, instead of potential difference, it would be the current multiplied by the resistance multiplied by the charge. And I hear the bright spark at the back of the class going, but I can change the charge. Yes, you can. And then your formula would look like this. Current squared multiplied by the resistance multiplied by the change in time. Why squared? Because there you've got the current multiplied by time, which I've substituted in there. Current multiplied by current is going to give you current squared. These are all accepted formulas that we can use in our calculation. Always make sure that you go and you look at the information that is given beforehand. If they give you the information and they give you the charge, then don't go and look for the charge or recalculate it. Use the values given to you in the text or in the problem when we start dealing with that. This is the overview for electricity. Let's go and look at some of the example problems that we have set aside for you for this section. Question 1. They tell us that a battery with an EMF of 24 volts has no internal resistance. You would have noticed that we have not covered internal resistance. That forms part of a later topic. It is connected in a circuit as shown in the diagram, and the resistance of the ammeter is negligible. Remember over here, ammeters have a very low resistance. The reason why they have such a low resistance is to make sure that they do not influence the current inside the circuit. Remember, the ammeter wants to measure the current and the charge particles moving in there. It does not want to influence and take away any of the values from any of the other components. All right, so your current will move from positive to negative. Over here we will see it goes through our first branch and it goes back up. And we have a second branch, and there the current goes through that section. Now, before we start doing any calculations, one of the key things you should notice over here is that this resistor carries the charge from both of my branches. So the ammeter reading for this resistor would be equal to the total ammeter reading for the entire circuit. My current will not split up as it does with the other two branches. Let's move forward to the questions. Question 1, they want us to go and calculate the total resistance of the circuit. Now, let's just start on a clean slate. You have got a parallel connection over here, and this parallel connection joins up with a series section on this side. So that section is in series and these two are in parallel. Your strategy over here would be to go and first calculate the parallel connection, because once you have the parallel connection, this becomes like one small resistor inside the series circuit. So we're going to start off with that, and we're going to do it this way. 1 over R parallel. You would notice that I sometimes fluctuate between using the parallel symbol that we have in maths or the P. Both of those are accepted. Again, as I said, choose footnotes that suit your working out. If you want to write out the word parallel, you are more than welcome to. Both of these footnotes refer to a parallel circuit. And write down the formula as it appears on your formula sheet. Resistance of resistor 1 plus resistor 2. You can go and label these individual resistors. We'll call this resistor 1, we'll call this resistor 2, and now we can start filling it in. Remember the second step, invert so that you have parallel resistance as the subject of your equation, open your bracket and rewrite everything. 1 over R1, R1 has a value of 6, plus 1 over R2, which is a value of 12. Close the bracket and invert. Once you have done that, we can bring up our calculator and we can clear it from the previous calculation and now go through the steps. Open the bracket. You might choose to work with the fraction function on your calculator, or you can use the division as I have. Let's just for interest use the fraction component over here. Then it would be 1, maneuver it down, divided by 6, plus, whoops, go back. See, those of us that are used to the old calculators still struggle with these ones. All right, and the new fraction would be 1 over 12. Move out from the fraction, close your bracket, and now you go and you invert your calculation. See, now what you've got on your computer screen is exactly the same as the calculation that you have written down. Equal to, and your answer works out to be 4. So we're going to put it down that your final answer works out to be 4 ohm. Remember the unit, and we can go and double check ourselves. This value is smaller than either of the two values that you have in your original branch over here. All right, that was our first step. Second step, and you can go and number your steps. Second step would be to go and calculate the total resistance. Now the total resistance in this case is made up of the resistance for my parallel connection plus the resistance for my resistor in series. The values over here, we're going to use the 4 ohm that we just calculated on this side and say 4 plus the resistor in series, if we go back to our diagram, is also 4 ohms. So it is 4 plus 4. We don't need a calculator for that. That works out to be 8 ohm. So our total resistance for this entire circuit works out to be 8 ohms. Let's go back to see what the next question is. Question 1.2. Calculate the reading on the ammeter. Now, if we go and we look at the information given to us, they gave us right in the beginning the potential difference for the battery or the voltmeter that we would have had across the battery. So that together with the total resistance allows us to go and calculate the current. So that was question 1.1. Move on to question 1.2. We have the potential difference that was given to us as 24 volts, and we've just calculated the total resistance as 8 ohm. I like to call this my little shopping list, and if you have a shopping list, you can go to the shops and you know exactly what it is that you need to go and find. We need to go and find the current. Use your formula. V is equal to I multiplied by the resistance. Substitute the values. Remember to make sure that you substitute the values into their correct places in your calculation. Now current works out to be 24 divided by 8. We might need to use our calculator. So clear it from our previous calculation. 24 divided by 8. And that is going to give you 3. Hide the calculator, and it is going to be 3 ampere. Make sure that you use the correct unit over there. A good idea might be to underline or highlight your answer. It also helps the examiner or the marker when they look at your work to say, all right, this question is now complete. That is their final answer. We can move on to the next question. And while we're talking about moving on, let's see what question 1.3 is about. They want to know the reading on the voltmeter. Now, worth 4 marks, as you can see over there. The reason why we cannot go and say that the voltmeter reading over there is equal to the voltmeter reading for the battery, because remember, I gave you the rules and said in a parallel circuit, the potential difference remains constant. If you go back and you look over here, you would notice that there is a resistor in series. When you've got the resistors in series, the voltmeter reading or the voltmeter reading for that component is different than that for the entire circuit. So our strategy over here would be to go and find out what the voltmeter reading across this component is. Subtract that from your original voltmeter reading to find out what it would be in your parallel circuit. So let's go and look at that again. Our strategy for 1.3 is to go and find the voltmeter reading for our series circuit. And that is going to be the current multiplied by the resistance for your series resistor. Now remember, the current passes both branches, the green and the pink branch from our indication over there, both pass through that component, which means that because it is in series, it is going to use exactly the same current as the entire circuit. Nothing has split up. So we've got 3 amperes. The resistance for that component is 4 ohm. 3 times 4 will give you a potential difference of 12 volts. Now, if we go and we look at our circuit, the total potential difference is equal to the potential difference for my parallel connection plus the potential difference for my series component. Total potential difference was given to us as our 24 volts. The parallel is what they ask us. If we go back over here, there we see this voltmeter is connected in parallel over here. And this is the one that they want us to go and calculate. So add that to the potential difference for your series component that we just had, and that is going to be 12. Normal addition subtraction sum, your potential difference is going to be 24 minus 12, and that is going to give you 12 volt. Okay, so now we've got that value, and now we can go and safely say that for both of these components, if I were to go and put a voltmeter over here, this voltmeter would give me exactly the same reading as the one at the top, because now it follows the rule where it says voltmeter readings in parallel are exactly the same for both branches. Okay, 1.4. Calculate the current that goes through the 6 ohm resistor. All right, remember, when you deal with a parallel connection, the current is going to split up. And based on Ohm's law, your current will split up in the following fashion. If it's got a very high resistance, very few of your charged particles will be willing to go through that high resistor. Just imagine this. It's a hot day, we have athletics at school, and we decide to run a 100-meter race. And I give you guys the option. You can run a 100-meter race on a straight, flat section of the sports field, or you can run a 100-meter up the stairs. Come on, be logical. You're not going to want to run up the stairs because it is going to require a lot of energy. The same thing applies to your resistors over here. If you have got a very high resistance, only a small portion of your current will go through there because there is the inverse relationship between the resistance and the current. So the higher the resistance, the lower the current that will pass through there. So we will, from here, remember now the following information. The voltmeter reading over here is the same as the voltmeter reading over there. Your voltmeter stays constant, so the potential difference stays constant. You are changing the resistance. If the resistance decreases, it means that your current is going to increase. That is correct. Inverse proportionality, as the one decreases, the other one is going to increase or become more. We're going to use that in our calculation. So for 1.4, they're asking us for the current through the 6 ohm resistor. Again, pay attention at the footnote. You will see that I use a footnote that tells me what I am dealing with. The current over here is what I want. I know that my potential difference is that of the parallel connection. We just calculated that to be 12 volts. And the resistance for that particular resistor, if I remember correctly, we named it resistor number 1, is going to be 6 ohm. Potential difference is equal to the current for the 6 ohm resistor multiplied by the resistance of resistor 1. Potential difference is 12. Your current is unknown. So that's the one that we want to find. And there are resistors 6. So the current works out to be 12 divided by 6. And that gives us a whole 2 ampere. if we go back, remember the total current in the circuit was 3 amperes. Let's look at what happened over here. Here we have the lower resistor, 6 ohm, and that is the one with the higher resistance. The 6 ohm now carries 2 ampere of current. If my total circuit uses 3 amperes, it means that the higher resistor is going to carry only 1 ampere of current. And it follows Ohm's law. Lower resistance will carry the higher current. The higher resistance will carry the lower current. There are all of these little things that you can remember that will help you. Go double check yourself, apply the principles, and you can always verify your answers. Even if you don't have the exact answer, you can have a guideline as to whether your answer is moving towards the correct direction or not. Let's go to the next question. And the last question for this one. They want us to go and calculate the amount of electrical energy that is transferred by the 12 ohm resistor in 5 minutes. So they are asking us to go and look at how much work was done. When you do work, you consume energy. And that is exactly what they are asking us over here. The energy that is transferred or used by this particular component. So to our calculation sheet. They've given us the resistance as 12 ohm. They told us that the time is 5 minutes. Now remember, we work with SI units over here. So SI unit for time is seconds. Immediately do your conversion. In 1 minute, I'm going to have 60 seconds. Cancel out the minutes, and 5 times 60 is going to give you 300 seconds that we are going to work with in our calculation. What else do we know? Because it is a potential circuit, we're going to know that the potential difference over there is 12 volts. Let's bring up our formulas and look for a strategy. If you go and you look at the information given to us, you will see that it's almost kind of random. You've got resistance, you've got time, you've got potential difference. So let's look at a strategy to solve this problem. The formula given to us is that of potential difference is equal to the work done by the charge. We want to go and find the amount of work. You can go and manipulate the formula, or we can go and say, but charge is not given to us. We need to go and calculate the charge before we can substitute it into the formula. But in order for us to calculate charge, we need to have current, because charge comes from your current multiplied by the change in time. Time we do have. So let's find our current first. Potential difference for the parallel circuit is equal to the current for the 12 ohm resistor multiplied by the resistance for resistor 2. We've got 12. Your current over here is unknown. The resistance for resistor 2 is 12 ohm. Pay attention. And our current works out to be 1 ampere. Remember that we have already reasoned this one out. Go back to the top. We reasoned it out. Now we've just verified it by calculation. You are more than welcome to go and look at it that way. Alternatively, we could have also gone and said the following. We could have said that the total ammeter reading is equal to the ammeter reading for my 6 ohm resistor plus the ammeter reading for my 12 ohm resistor. This one was given to me as 3. We calculated that to be 2, and this one would have then automatically worked out to be equal to 1 ampere. They're trying to fit in the 12 over there. And therefore, the current in the 12 ohm resistor is 1 ampere. So there's more than one way of doing it. Find what is comfortable to you as long as it follows scientific principles. All right, otherwise you're going to make what we refer to as an error of principle. Now we've got the current, we've got the time, we can quickly go and calculate the charge. Charge is equal to current multiplied by the change in time. Gives us our 1 ampere. The time was 300 seconds, and that gives us a charge of 300 coulomb. Now we've got everything we need. They have given us the potential difference, we want work, and we've got charge. The potential difference for my parallel connection works out to be 12 volt. The work done, there's your charge, which is 300. You're going to multiply it across. So work is going to be your 300 multiplied by the 12. Just to make sure that we do it right, we use our calculator, clear it from our previous calculation. 300 times 12, and that gives us 3,600. And the unit for energy that we have over here is watt. No, it's not. The unit for energy for work done is joules. So that worked out to be 3,600 joules. And that is the unit for the use of energy. That's how much energy that particular component used up during your calculation, or the running of the motor, so to speak. All right, that was question number 1. Let's move on to question number 2. Now, looking at this question, you'll see that they give us a whole lot of text with all the information. Question 2.1 over here asks us to go and draw the circuit. So it's important that we go and we assess and make sure we know exactly what is going to be in our circuit and how it is going to be set up. They tell us that we have 3 1.50 volt cells. All right, these cells are connected in series. Series meaning that they will be connected one next to the other. They have negligible internal resistance. We have 4 identical light bulbs, and these light bulbs have a resistance of 3 ohm each. Now remember, they are identical, so all 4 of them will have the same resistance. Then they tell us that L1 is connected in series with the battery and an ammeter. So you're going to have to include an ammeter in your diagram. And L2 and L3 are connected in series in a parallel branch. That seems almost like a bit of a trick question. So we're going to have a parallel branch, and these two will be connected one after each other in that specific branch. And then light bulb 4 is connected in second parallel branch, and we've got voltmeters 1 and voltmeter 2. Voltmeter 1 is going to be connected across our cells, and voltmeter 2 would be across light bulb 4. I've cheated a little bit, and I've already gone and drawn the diagram. So if we look over here, there are 3 cells. They are connected in series. We've got our ammeter that is connected in series with light bulb 1. Remember, light bulb 1 has a resistance of 3 ohm. Then we've got our first parallel branch. Light bulb 2 has got a reading of 3 ohm. Light bulb 3 has got a reading of 3 ohm. Light bulb 4 is on our second branch, also has a reading of 3 ohm. And there we've got voltmeters 1 and voltmeter 2 at the bottom here that is connected over these ones. Always make sure when you do your drawings like this that you use the correct component setup drawings that we use inside our circuits. You would see that for the light bulbs it is a circle with a cross in between. A resistor is a rectangle that we insert there. We don't use some of the other drawings that you have, so we're not going to have a little squiggly line with a circle around it. That's going to be completely wrong. Stick to the correct component circuits that we have over there. All right, so that would then be the sketch that you've drawn, indicating the cells or the battery, the ammeter, the different light bulbs as they were set up, the voltmeters as they are indicated, and now we can go and do the rest of the calculation from here. Question 2.2 asks us to go and calculate the reading on the ammeter. Now, we're going to have to do 2 calculations to get to our final answer. We have the potential difference for the entire circuit, which is our total potential difference. And we get that from the number of light bulbs. We've got 3 light bulbs that have the same value, so we're going to work that out. We can go and calculate the total resistance for the circuit. You've got your parallel and your series connection. We can work that out, and that will allow us to calculate the ammeter reading for the entire circuit. So let's move on to our calculation. Let's just get rid of that. Now, our total potential difference comes from the 3 cells that we have, and each cell has a potential difference of 1,5 volt. So your total potential difference works out to be 4,5 volts for this circuit. We are going to use that information together with our total resistance over here. Now remember, the total resistance would be the series connected light bulb and then the 2 light bulbs over there. Strategy over here. Go and calculate the resistance for these 2 because they would be in series. Then once you have done that, your second step would be to go and calculate the parallel resistance. And once you have that, you're going to add the parallel resistance to the series resistance to get your total resistance. So let's go and do those calculations first. Now, the series connection within the parallel connection is light bulb 2 plus light bulb 4. Now I'm lying to you guys. That would be light bulb 2 plus light bulb 3, and that would be 3 ohm plus 3 ohm. So that particular branch of your parallel connection has a resistance of 6 ohm. So if you go back up over here, this resistance would therefore be equal to 6 ohm. So now you've got a 6 ohm resistance, there you've got a 3 ohm resistance. Let's go and calculate our parallel resistance. We'll do that with blue. 1 over your parallel resistance is equal to 1 over the resistors that you just calculated in series plus 1 over light bulb 4, which we'll call resistor 4 for now. You are more than welcome to go and call it light bulb 4 just to keep continuity. Remember to invert in your second step, use your brackets. That would be 1 over 6 plus the 1 over 3. Close the brackets, invert. Alright, so we're going to pull up our calculator and work out over there. Remember, open the bracket. Your calculator is going to display everything that you've written over there. Fraction again for those of you that are comfortable with it. 1 over 6 plus fraction 1 over 3. Move out of your fraction, close the brackets, and invert your calculation. Now when you get to your answer, that answer is exactly what you need to go and write. So you're just going to say over there, it is therefore 2 ohm. Okay, now we can go, we've got our resistor in parallel. Let's go back to our circuit. We now have this parallel resistance. We can go and add that to that series resistance over there, and we will have the total resistance of the circuit. We're a reminder that we already have the potential difference for the circuit, and we can use that to calculate the current. So go back, that would therefore be your total resistance. It's going to be the series connection plus the parallel connection, and that would therefore be your 3 ohm from that light bulb number 1, plus the 2 ohm for your parallel connection, and that works out to be 5 ohm. Just in case I confuse some of you, let's make this series one over here series in parallel so that it's different from the series over there. So this would be your series connection within the parallel branch so that you guys don't get confused over there. Okay, and now to go and calculate your current. Total potential difference is equal to the current in the circuit multiplied by the total resistance. Total potential difference was the 4,5 that we had at the top. Current, and the resistance is the 5 that we have over here. So your current is going to work out 4,5 divided by 5. Use your calculator, clear it from your previous calculation, and that would be 4.5 divided by 5, giving you an overall answer of 0.9 ohm. Ampere. 0.9 ampere. Okay. Important over here, remember to go and write your unit. That unit is going to provide you with the mark. We don't give you a mark for just the correct answer. It must show the correct unit. And that was question 2.2. Let's see what question 2.3 asks us to calculate. They want us to know what are the readings on voltmeter 1 and voltmeter 2 respectively. Okay, for voltmeter 1, that is going to be quite easy. We are going to look at the previous calculation that we did over here, in fact. Sorry. Okay, previous calculation that we did over here. Remember that voltmeter 1 on this side is going to give us the potential difference for the batteries. So voltmeter 1 is simply going to be equal to the total potential difference in the circuit. And that comes from the three batteries with a potential difference of 1,5 each, and that works out to be 4,5 volts. Easy peasy. Okay, if we now want to know what the potential difference in voltmeter 2 is, we're going to apply a similar principle than we applied, or that we applied to question 1. Remember, we know the current through this light bulb. We know the resistance in this light bulb. If we therefore go and calculate what the potential difference for this light bulb is, we would automatically know what the potential difference in each one of these branches would be. So we're going to use that information, and we're going to say that the potential difference for my series connection is going to be the current for the entire circuit multiplied by the resistance for light bulb number 1. That is an L. Okay, let's write it neatly so you guys can see. For light bulb number 1, the current in the entire circuit we just calculated to be 0,9 ampere. The resistance is 3 ohm. 0,9 times 3, put that in our calculator, all clear. 0.9 multiplied by 3 is going to give us 2,7. So the voltmeter reading for that component is going to be 2,7 volts. So therefore, you would say that the total potential difference is equal to the potential difference for the series circuit plus that of the parallel circuit. And this was 4,5. 2,7 for our series connection, which is what we just calculated over here, plus the unknown potential difference that each of our parallel branches would have over there. 4,5 minus the 2,7 is going to be equal to the parallel connection potential difference that we have over there. I'm too lazy to calculate that, so we'll work that out. 4.5 minus 2.7, and that is going to be 1.8. So your potential difference across the parallel connection is 1,8 volts, and this potential difference is also equal to voltmeter 2's reading. So that is your final answer. Because remember, each of these branches, if we go back, the potential difference for this branch is going to be exactly the same as the potential difference for that branch. So therefore, the potential difference for the parallel connection would equal to that of voltmeter 2. Last question. Predict what you would observe about the brightness of the bulbs. Explain your answer by doing some calculations. If we go and we look at the connection over here. Now I know the diagram is starting to look very colorful, but just bear with me. Your current is going to leave the battery over here and go through the first light bulb, which means that already some of the energy is being used up. When it reaches the parallel connection, that energy is going to split equally to each one of the branches. So light bulb 4 as well as light bulb 2 and 3 would receive exactly the same amount of energy, but light bulb 2 would use energy before light bulb 3 does. So the energy that comes to light bulb 3 would already be less. So by looking at this diagram, we would see that light bulb 1 is going to have more energy, so therefore it would be brighter. Light bulb 4 would have more energy than light bulb 2 and 3, so therefore light bulb 4 would be brighter than 2 and 3, but dimmer than light bulb 1. And light bulb 2 and 3 would shine with equal brightness. let's go and see if we can do a calculation over there to verify those results. Okay, what is going to be our measurement over there? We're going to look at the energy that is used up by each one of these light bulbs. Now, if you go and you look over there, the measurement of energy is going to be our potential difference. So for light bulb 1, we just calculated that one. If we find it over here, for light bulb 1, the potential difference over here was 2,7 volts. So light bulb 1 uses 2,7 volts of energy is used over there. If we go and we look at light bulb 4, light bulb 4 is going to use the energy for the parallel connection. Now light bulb 4 is going to use 1,8 volts of energy that is used. Light bulb 2 and 3 will be a different scenario. Light bulb 2 and light bulb 3 are connected in series. So if we just look at that specific branch over there, okay, if we were to insert a voltmeter over here and a voltmeter across this one, and this is light bulb 2, that is light bulb 3, we'll call it voltmeter A and voltmeter B, okay? Now remember, the current that goes through each one of these light bulbs is exactly the same, but the potential difference will differ. Because the light bulbs are identical, in this case, the potential difference will split up between the two. So what we're going to do over here is the following calculation. We're going to look at the current that passes through the parallel connection. The parallel connection, I'm just trying to find the value over here from a previous calculation. Doesn't seem to be there, so we're going to do a calculation on our own. The branch over here, the total resistance for that branch is going to be 3 ohm. We know that the potential difference for the parallel connection works out to be 1,8. The current for your parallel connection is unknown, and the total resistance for the series connection in parallel is going to be your 3. So we've got 1,8, your current through that branch, multiplied by the resistance, which was 6. So it's the 3 ohm here, plus the 3 ohm there, and that is where I get my 6 for that side. Okay, so your current is going to work out 1,8 divided by 6, and that is going to give you a current of 0,3 ampere through this branch. Now if you use that 0,3 ampere, that is going to be the current for light bulb 2 as well as light bulb 3, and that gives you your potential difference for A. Let's just change that. Your potential difference for A is going to be equal to the current through light bulb 2 multiplied by the resistance for light bulb 2. So that is going to be your 0,3 multiplied by your 3 ohm resistance, and that is going to work out to be 0, let's verify that, 0.3, delete, 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 0.3 multiplied by 3, it's going to give you your potential difference of 0,9. So potential difference works out to be 0,9 volt. And remember, voltmeter A is going to be identical to voltmeter B, and that both of them will therefore be 0,9 volts. So if we go back to what we had over here in the beginning, light bulb number 1 uses 2.7 volts of energy. Light bulb number 4 uses 1.8 volts of energy. Light bulb 2 and light bulb 3. Let's write that properly. So light bulb 2 and light bulb 3 will use 0,9 volts of energy. And what did I predict in the beginning? Light bulb 1 would be the brightest. Light bulb 4 would be the second brightest, with light bulb 2 and 3 having the same intensity of light, but they will be dimmer than either light bulb 1 or light bulb 4. Let's see, question 3. Theo used the following circuit in an investigation to determine the relationship between resistance and current in a circuit. He first connects the bulbs in series and then in parallel. From your knowledge on series and parallel connections, you should remember, once they're on a parallel connection, your total resistance decreases. So you can already start forming an idea of what Theo is going to encounter in this problem. The EMF of each cell is 1,5 volts. And the resistance of bulb A and B is 2 ohm and 3 ohm respectively. A was given first, so A will be 2 ohm. B was given second, so that would be 3 ohms. This is the circuit that they provide for us. So we've got voltmeter 1, which is connected across our battery, a voltmeter across each one of these cells. Cells are or the light bulbs are labeled A and B, and we're going to look at the information over there. What is the reading in voltmeter 1? So let's go to our calculation sheet. Remember, they tell us that each cell has a value of 1,5 volt. Let's just include our information. They said that light bulb 2 has got a 2 ohm resistance and light bulb 3 has got a 3 ohm resistance. So question 3.1, they ask us, what is the reading on voltmeter 1? Voltmeter 1 is the voltmeter attached to your batteries. You've got 1, 2, 3 cells over here. So it is going to be 3 times your 1,5 volt, and that is going to give you a potential difference of 4,5 volts. Now, ladies and gentlemen, remember, when we have a single energy source, it is referred to as a cell. The moment we start putting 2 or more cells together, either in a serial or parallel connection, then we refer to it as a battery. So in this calculation, our battery is made up of 3 cells. That is why it's the 3 times the 1,5 that will give you the 4,5. The follow-up question to that, they want to know what is the reading on voltmeter 2 and voltmeter 3 respectively. Now remember, voltmeter 2, voltmeter 3, they are the ones that are connected over here across light bulb A and across light bulb B. We will need to know what the total resistance is for the circuit so that we can go and calculate the current. This is a very nice circuit. If you go and you look at it, we've got a series circuit, so no current splits up. That tells us that the current that we have in light bulb A is going to be the same as the current that we have in light bulb B. Let's go to our calculation sheet. From our information, we know that the total potential difference for the entire circuit is 4,5. We can quickly calculate the total resistance for the circuit by adding the resistance for light bulb A plus the resistance for light bulb B. Adding these two together, we will see that it is 2 ohm plus 3 ohm. That gives us a total resistance of 5 ohm. With this information, we can go and calculate the total current in the circuit. And that would be your 4,5 unknown current and your resistance of 5 ohm. So your current works out to be 4,5 divided by 5. From our previous calculation, we will remember that 4,5 divided by 5 is 0,9 ampere. Now that we know what the current is, we can go and use that information to go and calculate the individual potential difference for each one of these light bulbs. Because the current that goes through each one is exactly the same, it is the same value that we use for each. So your potential difference for voltmeter 2 is going to be the current multiplied by the resistance for A. Now, current is 0,9. Your resistance over there is going to be 2 ohm. 0,9 multiplied by 2 is going to give you a reading of 1,8 volt. We can follow exactly the same step for voltmeter 3. Is again going to be the current multiplied by the resistance, this times for light bulb B. The current is 0,9 multiplied by the resistance, which is 3 ohm. 0,9 times 3 is going to give us 2,7 volts. You could have solved the value calculation over here in this way, or you could have gone and done an alternative. All right? Now the alternative is just, I like to include it just so that you have an idea of what is happening, that there is another way of doing this. The total potential difference is that of voltmeter 1 plus voltmeter 2. Voltmeter 1 has been given to us, we calculated that as 4,5. We just calculated voltmeter 1 to be 1,8. So we can go and calculate the reading for voltmeter 2 from this information, whereby 4,5 minus 1,8 is going to give us our voltmeter reading over there of 2,7 volts. Now they would both give you the same answer, same number of marks. All you've done is you have applied the principle that the total potential difference in a series circuit is equal to the sum of all of the potential difference or all of the voltmeter readings inside a series circuit. Theo now connects the bulbs in parallel. Now remember, when he does the parallel connection, immediately he reduces the overall resistance in the circuit. So your resistance for the circuit is going to decrease. They want us to first of all go and calculate the resistance for the circuit, and from there we'll look at how that affects the current. So onto our information calculation sheet. Parallel resistance 1 over, your parallel resistance is equal to 1 over resistor A plus 1 over resistor B. So we're dealing with the inverse of these values. Immediately go and invert your parallel resistance. Open the brackets, so that would be 1 over 2 plus 1 over 3 ohm. Close the bracket and invert it again. All right. Let's go and use our calculator to find our answer over here. Open your brackets. Remember that it is 1 over 2 plus 1 over 3. Close the bracket and invert your calculation. Remember, what you see on the screen is going to reflect what you have just written down. Work your answer over there, 6 over 5, and work it to a decimal, which is 1,2. So your total resistance over here is going to be 1,2 ohm. Just a reminder of what I said right in the beginning, your total resistance in parallel is less than that of your smallest resistor. The smallest resistor was resistor A, which has got a 2 ohm resistance, and your total resistance over here is smaller than that of resistor A, which is 2 ohm. Okay, once we've done that, we can go to the next question. And over here, they now ask us for 3.5 to go and calculate the current that we now have in the circuit. So they first asked us to go and look at the resistance, and now we want to see what effect the resistance has on the current over here. Let's just correct that numbering. That was number 4, and we're now going to look at 3.5. So we're dealing with the parallel connection and the resistance for the circuit. So the total parallel resistance over here, the total potential difference has stayed the same. We now want to know what the current is, and we're going to look at our total resistance, which is that of the parallel resistor connection that we have over there. 4,5 is equal to your unknown current. We've just calculated this to be 1,2 ohm, and your current is going to work out 4,5 divided by 1,2 into your calculator. Clear it from the previous calculation. 4.5 divided by 1.2, and your answer works out to be 3.75. And that is ampere. If you go and you compare this to the current that we calculated over here in question 3.2, you would see that for a series connection, the current is 0.9, whereas the parallel connection, where the resistance was significantly less, your current was already higher. And I almost think that's what the next question asks us, is to go and look at the relationship. They want us to go and now go and write an investigative question. Remember, when you deal with a question, questions must end with a question mark. Otherwise, it's not a question, but a statement. Also, go and look at words that we use in questions. What, how, why. If you start your question with this, it is going to lead to the correct answer, because you start off with a question word, question noun, and you're going to use that together with a question mark to formulate the question. Now, what were we looking at? We were looking at the resistance and the current. So there has to be a relationship between those two. We also compared a series circuit with a parallel circuit. So when we go into our answer, our investigative question should include those factors that we looked at over there. So you're going to start a question over here with, let's start with what? What is the relationship Remember, they ask us for the relationship between resistance and current. So it is between the resistance and the current. In a series and parallel circuit respectively. So this question over here has everything we're looking for. We're looking at the relationship between your resistance and the current. And we are comparing a series and a parallel circuit within each other. I wish you all luck with this section. Exams are coming up, and I'm sure that you guys will, after this, be confident to approach any electrical circuit question. Just remember the basics. Use color as much as possible. Go and highlight, go and underline. Follow through the circuit so you can see where the current goes. Make sure that you remember the basic rules. When it comes to parallel circuits, your current is going to divide. The potential difference across the parallel connections will be equal. The total resistance is inverted, and therefore the resistance in a parallel connection is less than that for the smallest resistor in the total circuit. In a series connection, your current does not split up, so your current, your ammeter reading throughout is going to be the same. Your resistance will split up. The sum of all your resistors is equal to the total resistance, and your potential difference will divide up according to each resistor. Keep these things in mind. Study hard, work hard. The more you work on these ones, the easier they become. Thank you very much.